Forget everything you know about revolutions. The most important one didn't change flags or borders. It changed reality itself. It turned humanity from the center of the universe into a speck of dust hurtling through infinite space. And you know what? It was the best thing that ever happened to us, because only then did we begin to truly understand where we live. This is a story about titans whose ideas shone brighter than the stars, about geniuses who gave us the scientific method and laid the foundation for everything we call progress. In this video, you will learn why Copernicus was afraid to publish his main work, while Galileo was not, and how it ended for them. How Tycho Brahe, without a telescope, collected data that revolutionized astronomy. What makes Newton's laws so brilliant, and why they still work for launching missions to Mars. And how 17th century astronomers, physicians, and mathematicians laid the groundwork for 21st century technology. This wasn't just a series of discoveries. This was the scientific revolution, and its story begins right now. In the 16th and 17th centuries, European science reached new frontiers. Leading thinkers, by exploring the universe with scientific instruments, painted an entirely new picture of the cosmos and humanity's place within it. The scientific revolution was made possible by a dynamic and developing society that had already achieved significant technological progress. Firearms, gunpowder, and ocean-crossing ships allowed Europeans to discover, explore, and map a significant portion of the world. The invention of the printing press meant that any documented information quickly became available to scholars across the continent. Beginning in the 16th century, the interconnection between society, science, and technology grew ever closer, as progress in one field of knowledge spurred development in others. The path to progress. With the exception of a few brilliant discoveries, scientific thought in the late Middle Ages lagged behind technological invention. Technology dealt with practical things that either worked or didn't. Science, on the other hand, studied the nature of the universe and the laws governing it. Groundbreaking ideas often met with fierce resistance. In particular, new theories came into conflict with religious dogma in explaining natural phenomena, which were considered blasphemous and unacceptable to question. Until the 16th century, considered the beginning of the modern era, the prevailing view of the universe was based on the theories of the ancient Greek philosopher Aristotle, and further developed by the Greek astronomer Ptolemy. The teachings of the Greeks and Romans had always held great authority in the Western world, especially if they were acceptable to the Church. The Church had adopted Ptolemy's description of the celestial sphere, which placed the Earth at the center of the universe. In this system, which remained unchallenged until the theory of Copernicus, the Moon, Mercury, Venus, the Sun, Mars, Jupiter, and Saturn all revolved around the Earth. This arrangement corresponded with Christian theology, which made the drama of the fall of man and the salvation of the soul the cornerstone of history. According to Ptolemy, the Sun, Moon, and planets revolve around a stationary Earth. When scientists making astronomical observations found contradictions in Ptolemy's system, the orbits of the planets were redrawn, acquiring a very intricate appearance solely to fit the theory. It was understood that the Earth itself was the object of these corrections, while beyond the Moon, the crystalline planetary spheres and the starry celestial vault, guided by angels, were believed to be immutable and incorruptible in their perfection. Somewhere beyond them lay paradise and God himself. Not all scholars shared Ptolemy's view, yet it went unchallenged throughout the medieval period. The first carefully elaborated alternative theory was presented by the Polish scholar Nicholas Copernicus, who, as a cathedral canon, dedicated most of his life to scientific research. Although by no means all hierarchs of the Catholic Church were opposed to new ideas, Copernicus seems to have been aware that his conclusions could be deemed heretical. Therefore, he was in no hurry to publish his work on the revolutions of the heavenly spheres, and it is said that he saw a printed copy of it only on the last day of his life. The scholar who supervised the book's publication was so frightened of the possible consequences that he stated in the preface that the work's purpose was to aid astronomers in their calculations, not to critique Ptolemy's theory. A new image of the universe. In reality, Copernicus proposed a revolutionary new model of the universe, radically different from the one known at the time, as was later vividly depicted in 17th-century Dutch manuscripts. He argued that the Sun is the stationary center around which the planets revolve, and that the Earth is one of these planets. As the scholar himself, who proved this through precise mathematical calculations, wrote, "In the midst of all, the Sun resides." The period of our planet's revolution around the Sun is 1 year. Furthermore, it rotates on its own axis, completing a full turn in a day. The scientist also believed that the Moon was not one of the planets, as was thought at the time, but a satellite of the Earth. Copernicus was the first to place the planets in their correct order of distance from the Sun, Mercury as the closest, and Saturn as the most distant. Uranus, Neptune, and Pluto had not yet been discovered. The new theory was largely correct, but it had its weaknesses. In particular, the system was almost as complex as Ptolemy's, mainly because Copernicus mistakenly believed the planets' orbits were circles. Although Copernicus's theory was not yet definitively confirmed in his time, the outdated picture of the world was rapidly collapsing. A significant blow to these erroneous ideas was dealt by the Danish astronomer Tycho Brahe, who in 1572 observed a supernova, an immeasurably distant and very bright star whose appearance in the unchanging space beyond the Moon should have been impossible. A few years later, Brahe observed the equally incredible appearance of a comet. Through extensive and systematic observations conducted at his advanced observatory in Nuremberg, one of the first scientific centers of the new era, the researcher determined the positions of many celestial bodies and published the first modern star catalog. Even more impressive and convincing data were obtained by the Italian scientist Galileo Galilei. He was fortunate as he was able to use a new technical innovation, the spyglass, invented in Holland around 1600. Almost immediately after hearing of its existence in 1609, Galileo constructed his own, much more powerful telescope with 32 times magnification. His discoveries, including sketches of lunar craters, were of immense importance. Among other things, Galileo established the existence of countless stars invisible to the naked eye, spots on the Sun, the moons of Jupiter, and the phases of Venus. These studies debunked the theory of an unchanging universe and confirmed Copernicus's conclusions. Galileo used his discoveries to support the heliocentric, sun-centered theory of Copernicus. However, the Church sounded the alarm, as this threatened the traditions and authority of biblical teaching, which was based solely on a geocentric, earth-centered theory. For example, Joshua, as told in the Bible, stopped the sun's movement across the sky. Consequently, Copernicus's description of the sun as a stationary object in space had to be false and erroneous, as it was proclaimed in 1616. A European sensation. The Pope himself forbade Galileo from defending the views of Copernicus, and the scientist fell silent for many years. But gradually, he concluded that if he acted cautiously, his fame could protect him from persecution by the Church. In 1632, Galileo published the treatise Dialogue Concerning the Two Chief World Systems, in which he refuted the tenets of the Ptolemaic system. However, he maintained the appearance of following the Pope's instructions by ending the book with the assertion that the works of God's hands are not truly accessible to human understanding. But Galileo's work caused a sensation in Europe, and his ruse was exposed. The 69-year-old scientist was ordered to appear in Rome, where he was tried by the Inquisition and accused of heresy. Under the threat of a death sentence, Galileo admitted his error and announced his repentance. By the standards of the time, the punishment was relatively mild. Galileo was placed under house arrest for the remaining 8 years of his life. It was not until the 20th century, more than 3.5 centuries later, that the Catholic Church gradually reviewed Galileo's case, and in 1992, Pope John Paul II officially acknowledged that the scientist's condemnation was a tragic error. The Church's attempts to ban Copernicus's theory failed, as Galileo's book was translated into many languages and became popular throughout Europe. Moreover, crucial evidence for Copernicus's claims was provided by the German astronomer Johannes Kepler, 1571 to 1630, who, between 1609 and 1619, discovered the three laws of planetary motion. Copernicus and Galileo believed that planets revolved around the Sun in circular orbits. Kepler determined that the planets' orbits are elliptical, thereby eliminating the errors of his predecessors. He demonstrated that the heliocentric theory was simpler than Ptolemy's system and free from its contradictions. Today, 4 centuries later, these same laws of Kepler form the basis of all celestial mechanics and are used to calculate the trajectories of artificial satellites, spacecraft, and interplanetary probes. A few years later, Kepler created the Rudolini tables, which made it possible to predict the future motion of the planets. Based on the work of Tycho Brahe, these discoveries marked the beginning of a comprehensive and mathematically precise description of the solar system.
The laws of Newton. The Englishman Isaac Newton, 1642 to 1727, was the greatest scientist after Galileo. His work, Philosophiae Naturalis Principia Mathematica, 1687, convincingly demonstrated that the terrestrial and celestial spheres obey the same laws of nature, and that all material objects are subject to 3 laws of motion. Furthermore, Newton formulated the law of universal gravitation and mathematically substantiated the laws governing these processes. Newton's model of the universe remained virtually unchanged until the new scientific revolution of the early 20th century, which was based on the work of Albert Einstein. However, it is important to understand that Einstein's theory of relativity did not cancel Newton's laws, but rather refined them for extreme conditions, immense speeds and masses. For the overwhelming majority of terrestrial and near-Earth tasks, from building bridges to launching rockets into space, Newton's laws remain incredibly accurate and are used in engineering calculations every day.
Advances in medicine. In light of these discoveries, the role of scientific research grew even more significant. As dogmatic views faded and mysteries no longer seemed unsolvable, everything became an object of study, including the human body and its diseases. Until the 16th century, it was assumed that illness was the result of an abnormal balance of the 4 bodily humors: blood, phlegm, yellow bile, and black bile. The first to challenge this theory was the Swiss alchemist Paracelsus, 1493 to 1541, who argued that diseases were related to malfunctions of specific organs and could be treated with chemical remedies. Around the same time, the first thorough anatomical study of the human body was conducted by Andreas Vesalius, 1514 to 1564. However, the foundations of modern medical science were laid nearly a century later when the English scientist William Harvey, 1578 to 1577, discovered that blood circulates in a closed loop throughout the body, driven by the pumping of the heart, not the liver, as previously believed. This fundamental discovery laid the groundwork for all of modern physiology, cardiology, and cardiovascular surgery.
A new language. The new science sought to confirm the validity of observations through experiments and to translate the results into the universal language of mathematics. Galileo was the first scientist to realize that this approach was the key to understanding everything, stating that the book of nature is written in mathematical characters. The progress of the mathematical method was swift. By the early 17th century, common arithmetic symbols, addition, subtraction, multiplication, division, and equality, came to widespread use. A crucial step in this direction was taken by the French philosopher and mathematician René Descartes, who pointed the way forward by applying algebraic methods to solve geometric problems. Then, in 1614, the first adding machine, a distant ancestor of the computer, was constructed by Blaise Pascal, 1623 to 1662 in the 1640s. Furthermore, the research of this French mathematician formed the basis of probability theory, which allows for the study of unpredictable events. For example, although the result of a single coin toss is unpredictable, over many attempts, roughly an equal number of heads and tails will appear. 30 years later, the great German philosopher Gottfried Wilhelm Leibniz, 1646 to 1716, invented a machine capable of multiplication. Leibniz was also one of the creators of differential calculus, which became the most important mathematical method of the time. Isaac Newton independently arrived at similar results, and these two great men engaged in a dispute with far from scientific fervor over who deserved the credit for the discovery.
Inventions. By the 17th century, science had indeed advanced far. In addition to the telescope, instruments such as the microscope, thermometer, barometer, and air pump were invented. Scientific achievements continued to multiply. Newton discovered the wave nature of light and demonstrated that a beam of light that appears white is composed of a spectrum of colors, into which it can be separated using a prism. His famous experiment involved passing sunlight through a hole in a screen and a lens, causing the beam to refract and split into the colors of the spectrum. Two other famous English experimentalists were William Gilbert, 1544 to 1603, who laid the foundations for the study of electricity and magnetism, and Robert Hooke, 1635 to 1703, who introduced the term cell to describe what he saw through the lenses of a microscope he had improved. This seemingly simple act of observation and naming initiated cell theory, which today is the foundation of all biology, genetics, and modern medicine. The Irishman Robert Boyle, 1627 to 1691, invented a vacuum pump which he used with Hooke to conduct experiments studying the nature of a vacuum. He also formulated the law known today as Boyle's law, which establishes the relationship between volume and pressure. And the Dutch scientist Christian Huygens invented the pendulum clock with an escapement mechanism, proving Galileo's conclusion that a pendulum device could be used to keep time.
The spread of knowledge. During this time, interest in science was widespread, and scientific knowledge was not yet so specialized that any educated person could not conduct an experiment and make a discovery. Scientific societies were established, such as the Royal Society London, founded in 1662, and the French Royal Academy of Sciences, 1666. And scientific journals were published, like Philosophical Transactions, the first English periodical of its kind. The existence of scientific societies and journals meant that information about every scientific discovery could be rapidly disseminated throughout the country, allowing researchers to use the latest information. In other words, collaboration and the publication of research results accelerated scientific progress. As a result of this revolution in the 16th and 17th centuries, science became, and has since remained, one of the brightest examples of successful human collaboration for the common good. Key dates: 1543. Copernicus declares that the Sun is the center of the solar system. 1572. Tycho Brahe observes a supernova and, in 1577, a comet. Circa 1600. The telescope is invented. 1609. Galileo explores the heavens with a telescope. 1609 to 1619. Kepler's laws of planetary motion. 1632. Galileo's treatise, Dialogue Concerning the Two Chief World Systems. 1633. Galileo is arrested, accused of heresy, and convicted. 1642. Pascal's adding machine. 1657. The first scientific academy is founded in Tuscany, Italy. 1662. The Royal Society of London is founded. 1671. Leibniz's calculating machine. 1687. Newton discovers the law of gravitation. 1704. Newton describes the nature of light. And so, step by step, a handful of geniuses changed the world forever. Their main tool was not the telescope or the ruler, but insatiable human curiosity. That courage to ask, what if everything isn't as we're told? That was the true scientific revolution. This spark of curiosity that they ignited is the main engine of progress. Thank you for taking this journey with us. If you enjoy stories that connect the past with the present and want to continue exploring the great ideas that changed our world, support this video with a like and subscribe to the channel. It really helps us create new content. That's all for now. Stay curious and see you in the next video.